Okay, good. So these are the topics. And as I said before in the presentation this morning, it builds on APL and Ethernet to the field technology. So let's see what we talk about here. So digital twins in automation, really, given the fact that process automation systems are based on 4 to 20 milliamps analog values today, that's a big step forward. And the second question, therefore, also is, so what are the building blocks and how mature are they today? And as I said, it's largely based or a big reason to believe that this will come now, at least in newer builds, is the fact that we will have more Ethernet-based devices in the process automation world using APL and SPE. So what I want to share is these topics and these standards. So I'm from Germany, I'm based in Munich, and many of the things I will share are driven by and I'll share more who exactly, NAMUR, ZVEI, Profinet International, and a few more standards defining organizations. And these are the concepts that they've developed: Process X, NAMUR Open Architecture, Modular Type Package, and then the corresponding technologies, and that's what we'll go through now. Yeah, NAMUR, ZVEI, those are the two that I mentioned. They've been driving, putting together the ecosystem, the vendors, the users, and facilitating the discussion between the two very well in Germany. I'm sure there's other organizations doing similar things. In the US, for instance, there's OPAF, Open Process Automation Foundation, which are also doing a great job, slightly different focus. But I'll share with you what kind of the Central European, German-based ecosystems are working on. So what we saw this morning, Ethernet APL, is breaking that barrier down here. And this is what it looks like now. So single pair Ethernet, APL in the process automation world largely is providing the complete stack with Ethernet everywhere. So from field devices, controllers, engineering stations, operator stations, everything is based on Ethernet. And time-sensitive networking technologies are used to manage that network more and more in a more and more sophisticated way. So that's the future. That's what we're working towards, and hopefully it makes everything a lot quicker, easier, cheaper, and more powerful. As you can see, Ethernet APL is based on 10 megabits per second. Profibus and HART have been significantly slower, and that alone is a fairly measurable advantage of Ethernet APL over the current solutions. And just to say that the HART signal is just the overlay, so the diagnostics interface, if you like. The analog values are even slower, obviously. But I guess to some extent that's okay in process automation, where the control loops are not quite as fast as they are in factory automation or energy, as we heard before. So some of the things that the NAMUR, these two organizations did. NAMUR is the process control technology user group in Germany, but also many of the, for instance, US companies are participating there. ExxonMobil, Shell, also Dow, and a few more companies, and all the big German chemical and pharma companies and oil and gas are participating. And ZVEI is the Electrical and Digital Vendor Company Association in Germany, so the vendors, and this includes companies like Moxa and also the DCS system vendors like ABB, Honeywell, Emerson. All these companies are part of that group. And they have joined working groups together, and this is some of the deliverables that exist. So what are the use cases for the different phases of a project? All these things are very well documented. There's lots of PDF files on the web that describe how you can use it. And the first topic, Ethernet APL, I think we've looked at enough. the TCO analysis I mentioned at least this morning, is very clear. APL is already at the same level as remote I/O-based applications, and both of them are cheaper than trunk cable-based applications. So no reason not to use APL for new builds and significant independent expansions of existing plants. And if you're clever, if you have a clever maintenance projects, you can over time also replace old devices based on 420 milliamps with Ethernet APL devices. So enough about APL. Let's talk about the next layer up, and this is called NOAA. So the NAMUR, the Process Control Technology User Association, defined an open architecture, and the idea was to have actually, before I continue, has anyone heard of NOAA or NAMUR? Okay, one out of a couple, so then I'll explain it anyway, or my perspective on it, and feel free to jump in. So the general idea is that this gray bar is the core process control zone, and it stays intact. And then there's a NAMUR Open Architecture part, basically the IT, and you have a defined way to get data from in particular from the field devices in the core process control area, get it out, not through the control system, but independently as a second channel, and also a secure way back. So you use the data from the field, much more data than the control system normally uses, in particular asset information, diagnostic information, independent of the control system, as I said. Then you do monitoring and optimization, so clever analysis, and then you come to the insight that something in the control loop has to be tweaked a little bit, and then there's a secure way to get back. It's called verification of request. It's part of the NOAA concept. So you can send a request, and the control system then verifies that request and implements it, or says, no, not possible, physical constraints, tell me this is too dangerous, I'm not going to do it. But at least there's a controlled way out and back in for clever IT applications that sit outside the actual control system and optimize the process control operation. So, and this is different from OPAF. OPAF is kind of modular, open, everything radical new. NOAA is very much brownfield compatible. No surprise, in Germany, very few chemical plants are built from scratch again. So the focus very much is on brownfield, applies many of the Industry 4.0 ideas of digitalization, the industrial world, and so on. So let's have a look at that a bit. At first, what is the use case? So the use case is a lot about asset management of the field devices. There are the first document, or one of the first documents that they published, is what are the different actors in a chemical plant, for instance. And these are the use cases that they documented at great length to see what's the value and is it valuable to implement these types of concepts. So automated as built, for instance. The question is your current documentation of the plant accurate? So are all the field devices in your paper documentation for the operator the exact same devices that you think they are? So are the devices in the field really the devices that you have on paper? So if you replace a flow meter or pressure sensor maybe at 3 o'clock on a weekend in the morning, are you sure that the documentation is really updated then? And with Ethernet APL and the NOAA concepts of getting the data from the field devices via a second channel, you can automatically double check that. And what NOAA did is, okay, based on these use cases, what parameters do I need from a field device to be able to do that use case? So every parameter that's part of that NOAA concept will have to be justified that you need it, and all the parameters that you need are there. So this is the big work of, and it took years to do that, to create what's called PADIM. That's the data model for field devices in process control systems. And it says Process Automation Device Information Model. It's an OPC UA companion spec. Fieldcom Group is the owner of it, and OPC Foundation is the host of the companion spec. But the content and the governance, updating the model and so on, we're currently at version 1.0.2, is done by Fieldcom Group. And just to give you a bit of an idea, what else is in here? Unique identification is another use case. For instance, if you want to implement a firmware update, the first thing you have to know is what device is it actually? What's the vendor? What's the model? What's the hardware revision? What's the current firmware version? And a few more things. So these are the parameters that you need for the unique identification of the device in the field. Then you can get the vulnerability list, the new firmware from the vendor, and then implement it. And verification of request is going to come in there to update the firmware of the device. And then you can check again, did it actually update the firmware? And all this is a part of the NOAA concept. Okay, let's continue. So PIDIM is the data information model. What is the architecture? So here's a more functional architecture diagram. Not all the devices exist as they are on the table, on the diagram here, but the general idea is that you have field devices down here, can be field bus, can be Ethernet based, can be OPC UA Ethernet based, so Profibus, Profinet, OPC UA. And you want that OPC UA data from the devices, about the devices. In this case, it's easy. If a device, a field device has an Ethernet interface and implements the OPC UA protocol stack and is able to provide the data in the right format, PIDIM, then it can just go through and everybody is happy. You have to apply some security standards over there. There's a security gateway, lots of requirements around the security, a lot of it based on 62443, but even more specific. But what about the older devices? And that's actually quite a nice trick. And the main reason why NOAA could actually be successful, because it does include a mechanism to integrate legacy devices. So even if you have field bus devices or other devices, if you have a NOAA server, and this could be a remote I/O with a logic in it, it could be a protocol gateway that supports OPC UA, PIDIM, and then it can actually, if you have a mapping from the device values that you get down here into OPC UA based on PIDIM, then the upper level systems can treat it like a modern device. So that backwards compatibility, that's the brownfield compatibility that I mentioned earlier. So, and that's a very big reason to support NOAA. I guess the trigger to actually implement it is probably that you have APL, and it's easy to work on these topics once you have Ethernet-based devices. But once you start implementing some of the more sophisticated asset management and monitoring and optimization applications, there is a way to integrate some of the older values, some of the older legacy devices as well. And it's called NOAA server, could be a relatively simple protocol gateway. Okay. Before we continue, let's talk a little bit about the security. OPC UA is not the same as OPC UA. Some of you will have possibly tried to integrate OPC UA devices into your higher level OPC UA-based systems, and I would guess that typically that didn't work. Because OPC UA, if you don't have a defined data model and a defined transport model, then it's a bit difficult to integrate these things. So one of the things we're doing in that NOAA standardization groups is to say, what are the actual architecture types that we want to look at? And here's two examples. So you have client-server and pub-sub. I'll spare you the details here. And then you have security, none, sign, and encrypt. And these are all variables that you can or not use. So we, for now at least, picked OT standard, which is OPC UA client-server with no security. That already exists. Quite a number of devices supported. So that's a real, something that you can do today based on commercially available products, no problem. and pub/sub. Starting to emerge, at least some of the big DCS vendors like ABB and Siemens have implemented architectures based on pub/sub. Again, two variants there really, but the general idea is that this is an IT tested, well-known, mature mechanism that is also secure. So it is typically encrypted, and you can actually use that in this architecture. So this OPC UA is a very generic term, is all I'm trying to say, but you have to be a bit more specific what actually you mean by OPC UA, how you want to actually implement it, otherwise it doesn't work at system level. So now let's have a look at the data flow a little bit more. This is the lower part of the architecture that we looked at before. You still see the legacy device. This is a NAMUR-compatible device that has Ethernet and OPC UA implemented. And here you can see the parameters that you can get from PADIM. I think it's roughly 80 parameters today. I don't know how many use cases, maybe 10 or so have been defined. And from these parameters, you can select the ones that you need for a certain use case. So this one here is that I picked as unique identification, so trying to find out which device is it. And the most important parameter really here is the product instance URI. This uniquely identifies a model from a specific vendor. So you can start looking at things like, is there a vulnerability, is there a new firmware, and so on. Or also handover documentation, so the technical documentation, the manuals, the quick installation guides, whatever, you can also automatically get it once you have the product instance URI. And it is part of the data block that the device can share about itself, either directly as here, or with a NOAA gateway or NOAA server that has that mapping, for instance, Profibus data. There are mechanisms to get hard data over Profibus to such a gateway. So these solutions exist today and actually work surprisingly well in some cases. So you can automatically have that mapping. It's encoded or can be encoded in an FDI package. So then it automatically transmits the original hard data that's communicated over Profibus to the NOAA gateway and then translated into OPC UA, standardized data model. And then you have the same as if it was a new, fully compatible device. And then you can start communicating that data through the security gateway up into the MNO zone. So this is core process control, this is MNO. Basically, this is the OT zone and this is the IT zone. And then you have very standardized data, and whether the level meter or the flow meter is from ABB or Anderson-Hauser or whoever, it doesn't matter. It's always the same data model, and you can really get that in an automated, scalable way. Okay, PIDIM, if you want to learn more, is hosted by Fieldcom Group, and it provides on the OT side these standards on the left, and it translates it with the FDI package into OPC UA. By the way, if there's questions or comments, you don't have to wait until the end. If you have anything to share, then stop me anytime. Okay, this is the OT world. So APL and NOAA together already provide what I would say is already the data model for the digital twin of a field device. And once you want to share that across companies, OPC UA is typically not the right protocol to use. So I'm not sure if you've heard of Process X. That really is a bit of a German initiative. Manufacturing X, Catena X is used in automotive industry, Factory X. So lots of these X initiatives exist where you want to exchange data across companies. And Process X is the one for the process industry in Germany, and again driven by NAMUR, the process control technology user group. What is it? It's a data space. Who knows what a data space is? And I didn't know until last year, I must admit. Okay, good. So data space is kind of similar to a cloud-based data exchange across many users, just without the cloud. And what do I mean by that? So today, if you have, for instance, a big chemical park with different companies producing different things, and one company delivers stuff to the next one, you have energy providers, steam providers, and so on, that provide steam as infrastructure to all the companies over there. There's a number of reasons to exchange data across companies for instance, in a Verbund site or in a big chemical part. And today, and the reason why I said steam, that's the first use case that they worked out and presented. So how can you become more efficient in understanding when do you need how much process heat, how much steam do you need over the next few days? And this is typically done via email or phones sometimes. Is that, maybe you have 5 different big power plants in the vicinity of the chemical park that you can theoretically use to generate the power or process heat. So you call them. Do you have enough power? Do you need, and so on. You could use a cloud platform. That's not considered a good idea. At least in Germany, we're very security and data protection oriented. So nobody wants to do that. And the data space is the way that you find a common format of a data exchange and how to authenticate and so on. So there is a central piece that allows everyone to authenticate themselves, and then everyone can say, I want to share data with this company, I want to allow that in this format, and so on. And then the exchange of the actual data is entirely peer-to-peer. So it's not stored anywhere, it's just the infrastructure to exchange peer-to-peer data. That's called a data space. And one of the companies that is actually providing some of the infrastructure for it is the IDTA, the International Digital Twin Association, and its AAS, Asset Administration Shell, is the technology that they promote. Also, they have different data models. So digital nameplate, for instance, is one of the data models that they use that corresponds to the unique identification use case of PIDIM. So now that you have that product instance URI, you can put that in here, and there's no need to change the data format. Every parameter is clearly defined. So if you say, in PIDIM, OPC UA, this is the product instance URI. Everybody knows the semantics of that value. And in the digital nameplate, you have also product instance URI, and everybody knows what it is, so you just plug in the value. So you don't need to have another protocol converter or anything, because every parameter is semantically fully defined. The technology for that is called IEC CDD or E-class. So this is Common Data Dictionary. It's an IEC committee that defines these parameters. It's a library of parameters and what they mean. And every parameter in PIDIM and every parameter in the Asset Administration Shell has a semantic ID. So links to that Common Data Dictionary. So it's fully clear what it means, independent of language, format, everything. And this is now the reason why if the vendors have NOAA-compatible devices, you implement NOAA, you implement AAS, then you can exchange asset information across companies. And one of the use cases that I mentioned at the beginning was the firmware update. So if you think what the EU is mandating, Cyber Resilience Act, CRA, forces all the vendors to provide vulnerability information and firmware updates for their devices, including field devices. And this too requires all the operators to actually do something with it. This is a potential cycle of how to do these things. And Here's an example, a German Fraunhofer Institute in Magdeburg. They did this KI twin. KI is German for AI, so very clever name. And they built this factory model, and they have AAS all over the place, and underneath it is NOAA and PRDIM. And what they can do is they have what's called submodel templates. Those are the templates within AAS for all the devices over here. And really, when they exchange, this is the flagship use case, the device replacement. If they exchange, I think, I don't remember what they exchange as a standard use case, but let's say the flow meter from one company with another one, then the system automatically detects that now it has changed, and it has to use the FDI package from the devices automatically to integrate into the control system, into the asset management system. And number one, the control system continues to work as planned. And number two, the asset management system is updated automatically. So you really know exactly, and this is the automated as built use case that I mentioned before. So your plant documentation is automatically updated. And in this case, really for this particular use case, it's fully 100% automatic, including getting the new information from the cloud, from the vendor cloud. So I think one of the devices is Phoenix, and Phoenix Contact has Asset Administration Shell Server implemented as a demo or as a beta version already today. So they download the field device information from the vendor cloud. And so this really, including the cloud-based or internet-based exchange of cross-company information and firmware. Some of the files, I think it's more handover documentation, is already working in this use case, 100% automated. So in terms of maturity, I would say this is not production ready, but at least all the building blocks work together as intended. And I think by now there's a bit more of these use cases that demonstrate the value of this. What's the next steps? So Profinet International took ownership of NOAA. The NAMUR team thought it's too German. We want to make it international. And Profinet International still is a bit of a German, but not as German as the NAMUR organization. So they have some experience in standardizing, certifying equipment and so on, and taking it international. Actually, Profinet, far and away, PI really did a fantastic job in pushing Profinet into APL. So all the devices, all the APL field devices are based on Profinet today. So very impressive job there. And now the task from NAMUR is for PI to take it international. And there's different working groups and alignments with the originators of NOAA. But also here you see FieldCom Group, ODVA, OPC Foundation, PI, and yeah, I guess that's the most important one. So you see NAMUR, ZVI, VDMA, another German association. So this is being worked on now, and the idea is to make it to select the right standards, create test environments and test authorities or test agencies around the world, similar to Profinet, and take it international. And these are the different things that they're working on. So let's continue to dream a little bit more and think what's already possible. So back to that functional architecture. One of the areas, or one of the, to me, and this is now my personal opinion, one of the reasons why NOAA hasn't taken off quite as much as it should have, in my opinion, is the security gateway. The NAMUR team defined very specific, very tough requirements for the security gateway. Has to have 3 layers. One bottom layer is only collecting information. Then there's a unidirectional layer that physically only allows unidirectional traffic from the bottom layer to the top layer. Basically, the bottom layer is an OPC UI client that gets information from the field devices. Then there's this insulating layer, and then you have the top layer, which is basically an OPC UA server that the IT applications can pull to get information. So very specific use case, and there are hardware diodes available from companies like Genua or Genoa, Waterfall, and a few more companies that are used in military space primarily. In some cases, very highly critical transportation cases, but not in process or factory automation. And they're very expensive, they're very difficult to set up, and with a very complicated or very complex data model, it's expensive and very cumbersome to set up. So one of the things that we're currently working on, and I am leading the security team in that PI committee, so I'm involved in it. What I'm and other people are trying to do is, where can we simplify this? And here's one of the examples. So we have a next generation firewall that is capable, or actually a couple of them, that is capable of OPC UA packet inspection. And what we're trying to prove is that with this, you can ensure unidirectional traffic from the CPC, from the core process control zone, to the monitoring and optimization zone, just by looking at the packets. OPC UA is a bit of a complicated protocol, so you have session initiation in the beginning and so on. So there's a couple of, it's a bit more complicated than Modbus, where you can just say the read commands are okay, the write commands are not. Bit more complicated, but similar concept behind it. And then you can ensure that unidirectional traffic as well. And it's much cheaper, much simpler, totally transparent to the client and the server. And that's one of the simplifications that we're currently working on. And if you do these things, then the use case that I mentioned before, the firmware update, becomes possible already today. So I guess I will not go into the details how this works, but basically you have the field devices over here. You have the NOAA firewall, which is not allowed today according to the current official documentation. But if you relax some of the architectural requirements around the NOAA security gateway, you can get out over here, get the new firmware. If you determine the device, you think it should be updated, you can get the new firmware, and then through some way you can go back in, verification of request, and then update the devices in the field. So that's a theoretical use case we're looking to put into practice using the NOAA concepts. But what is already possible today, and I think this is something where Moxa is not the only one, but Moxa is one of the ones where you can actually do it, and that's you use the Moxa network management system, MXview 1 server, and that can actually connect to the Moxa server on the cloud. It knows about which firmware versions are available for all the devices it manages, and then it can actually do what is on the previous slide using Moxa proprietary, or at least not NOAA mechanisms already today. So if you have Ethernet APL-based devices, no, actually, this concept today, as we speak today, is possible for all the Moxa devices. So MXview 1 can firmware update the Moxa devices. In theory, it could also do other things for other vendors, but that's not implemented today. And maybe a last point. I will not go into too much detail, but the network management system also has a northbound interface. So in theory, you can integrate it into your higher level asset management system. And where you think of a human user that uses the web GUI, all these things you can also do through a northbound interface if you want to control it automatically from a higher level system or agent or whatever you want. Okay. But that's more a side note. What I did want to share today is the architectures driven by NAMUR primarily, in particular NOAA, and then the technologies involved in the whole stack from field device to field device vendor, through the end users and the vendors' IT systems. Those building blocks exist. I wouldn't say they're rolled out in a really big way. So I think the proof of the actual production systems over 10 years is still to be done. But at least conceptually, many of these things are already done, and at least in theory, super scalable. And last slide, this is how they fit into the overall ecosystem. So NOAA-compliant field devices provide asset management information via OPC UA companion spec, compatible with PRDIM. The parameters are semantically grounded in IEC CDD. Security is maintained via the NOAA security mechanisms, in particular, everything related to 62443. Intercompany exchange can be done with the Process X, the data space concepts based on Asset Administration Cell, AAS. Basically, that is the full stack, even cross-company, of secure digital twins of field devices in process automation environments based on fairly standard future-proof or industrial Ethernet technology. Thanks for now. Do you have any questions or comments?
Okay.
If not, I'm still here, so I'm curious. Thank you.
Thank you very much.